Right now, above your head, there is a place where your blood would boil and freeze in the same breath. A place where sunlight burns one cheek while the other turns to stone. We'll stand inside a nebula colder than any lab on Earth, walk through craters on the moon that have not felt warmth in billions of years, and drift toward the quiet edge of time where even stars give up. If cold space fascinates you, hit like and subscribe so you don't miss what comes after. Now breathe in. We begin. Imagine stepping outside your spacecraft without a suit. You expect to freeze instantly. You expect your skin to crack like glass. That's what every movie has told you. The truth is stranger and far more cruel. For the first few seconds, space does not feel cold at all. It feels like burning. Your skin tingles. Your eyes start to sting. The moisture on your tongue begins to bubble, not because it is hot, but because the pressure around you has vanished. Water cannot stay liquid in a vacuum, no matter the temperature. So, the water on your eyes, in your mouth, inside your lungs, starts to boil while you are still alive. This is confirmed by real accidents. In 1965, a NASA test subject named Jim LeBlanc was inside a vacuum chamber when his suit failed. The pressure dropped in an instant. Before he lost consciousness, he said the last thing he felt on his tongue was his own saliva boiling. He survived only because technicians reached him in 15 seconds. That story reveals the first secret of cold space. The cold is not the first thing that kills you. Here is why. In your kitchen, cold works by contact. You touch an ice cube, and heat flows out of your fingers into the ice. Your skin cools because billions of moving air molecules carry warmth away from your body every second. Cold, in the way you know it, needs matter. Space has almost no matter, no air, no wind, no molecules bumping into your body to steal warmth. So, even though the temperature reading in orbit near Earth is about minus 250 degrees Fahrenheit, that number is almost meaningless to a human body. There is nothing there to touch you. What does happen is slower and in some ways worse. Your body loses heat only through radiation. Your skin glows faintly in infrared, throwing warmth out into the dark like a dying light bulb. It takes minutes, not seconds, for that heat to drain. The horror movie version of a human flash freezing is pure fiction. But while you wait to freeze, other things happen first. Without pressure, the gases dissolved in your blood start to form bubbles. Your lungs, if you held your breath, would rupture within seconds. Your skin would puff up like a balloon, though not explode the way films suggest. And the unfiltered sunlight would burn any exposed side of your body with brutal radiation, giving you a deep sunburn in under a minute. So on one side, you are cooking. On the other, you are slowly bleeding heat into nothing. This is the real paradox of the vacuum. It is not a freezer. It is something the human body was never built to understand. Scientists call this environment thermally confused. Your body cannot decide if it is hot or cold because the rules that connect temperature to feeling have broken down. Without air, without pressure, without the steady flow of molecules, cold becomes a concept, not a sensation. That is the first lesson space teaches anyone who gets too close. The cold is coming. It is patient. It is waiting for the boiling to stop, and the deeper you go, the more patient it gets. Because the real temperature of empty space is nothing like what most people believe. Ask most people how cold space is, and they will say absolute zero. They picture a dead, frozen void with no heat at all, a perfect nothingness. They are wrong. Empty space, even in the darkest corners between galaxies, has a temperature. It is cold beyond anything on Earth, but it is not zero. It sits at about minus 455 degrees Fahrenheit. That is just under 3 degrees above absolute zero, the coldest point anything can theoretically reach. 3 degrees does not sound like much. In your kitchen, 3 degrees is the difference between frozen peas and slightly soft peas. In the universe, 3 degrees is everything. Those 3 degrees prove that even the emptiest place we know of is still glowing with warmth, a ghost of warmth, but warmth all the same. Where does it come from? It comes from the Big Bang. Around 13.8 billion years ago, the universe was born in a fire hotter than anything that has ever existed. As the cosmos expanded, that fire cooled. It stretched out across billions of light years, thinning like steam spreading through an empty hall, and the light from that ancient explosion never fully disappeared. Today, that light has become something called the cosmic microwave background. It fills every direction, in every corner of the universe. If your eyes could see microwaves, the sky would not be black. It would glow faintly, in every single direction, with the afterimage of creation itself. This is a confirmed discovery. In 1964, two radio engineers in New Jersey kept hearing a strange hiss in their antenna. They thought it was pigeon droppings. They cleaned the antenna. The hiss stayed. They pointed it in different directions. The hiss stayed. They had accidentally picked up the echo of the Big Bang, coming from everywhere at once. That faint glow sets the floor for the temperature of space. Nothing in the natural universe can be colder than the cosmic microwave background, because the background warms everything it touches, no matter how gently. It is a universal blanket, too thin to feel, too wide to escape. Think of the universe as a giant oven that was turned off 13 billion years ago. The oven is still cooling, the walls are still ever so slightly warm, and that warmth keeps the whole room from ever reaching true cold. But here is the part that should unsettle you. That background glow is getting colder every single year. The universe is still expanding, still stretching, still thinning out, which means in the far future, space itself will drop closer and closer to absolute zero. Not in thousands of years, not in millions, but in numbers so large the human brain refuses to hold them. We live in a warm chapter of the cosmos. Our sky is bright, our stars are young. The heat of the beginning is still with us, even in the darkest places. But the universe is slowly falling toward a cold we cannot imagine. And strangely, some places in the universe have already beaten it. There are objects out there right now that are colder than empty space should be able to get. Colder than the Big Bang's echo, colder than anything physics says a natural thing should be. One of those places is a dying cloud shaped like a boomerang. Let's slow down the worst 10 seconds of a human life. A suit tears open. The air rushes out. You are alone in the dark, with nothing between your skin and the universe. Second one, your eardrums pop hard. The pressure in your ears has nothing to push against anymore, so the air inside your head tries to escape. It does not burst them, but you would be half deaf for days if you survived. Second two, your lungs empty whether you want them to or not. Trying to hold your breath in a vacuum is the fastest way to die. The air in your chest expands, rips through the thin tissue of your lungs, and floods your bloodstream. Astronauts are trained to exhale immediately because an empty lung survives, but a full one explodes from the inside. Second three, your tongue and eyes feel warm, then tingly, then wet. The water on any exposed wet surface, your mouth, your eyes, the inside of your nose, starts to boil, not because of heat, because of pressure. Liquid water cannot exist in a vacuum, so it turns to vapor at whatever temperature it happens to be. Your saliva foams, your tears fizz. Second four, your skin begins to swell. Fluid in your tissues, once held tight by the pressure of the air around you, now pushes outward with nowhere to go. Your body puffs up to nearly twice its normal size. This sounds deadly, but the skin is a surprisingly tough bag. It holds. You inflate like a soft balloon, but you do not pop. That is a confirmed result from animal studies and from real human accidents. Second five, your blood chemistry starts to shift. Nitrogen, dissolved in your blood at normal pressure, starts fizzing out of solution, the same way bubbles rise in a soda can the moment you open it. This is called ebulism. Divers know a slower version of it as the bends. In space, it happens in seconds. Second six, the sunlit side of your body, if there is one, is already being scorched by unfiltered ultraviolet light. No atmosphere filters it. You could get a severe sunburn on one cheek while the other half of your face stays pale and cool. Second seven, consciousness begins to fade. Your brain is running out of oxygen. Unlike holding your breath in a pool, this blackout comes fast and clean. Most people lose awareness between 9 and 15 seconds after exposure. Second 8. Your heart is still beating. Your body is still warm. Nothing has frozen yet. Nothing will freeze for many minutes. The vacuum has no shortcut to cold. Second 9. Your muscles stop responding. You cannot move. You cannot signal for help. You are a soft shape, floating, inflated, slowly glowing with lost heat. Second 10. Black. This is the window doctors call the useful consciousness window. If someone pulls you back into a pressurized space within about 90 seconds, most of the damage is reversible. Past that, the body cannot be saved, but it still does not freeze solid for a long time. The truth is simple and horrifying. Space does not freeze you. It suffocates you first, then swells you, then slowly, patiently, drains your warmth into the dark. And on some worlds, that dark is close enough to touch in daylight. On the moon, the sun does something it never does on Earth. It tries to kill you twice, in opposite ways. At the same time, Earth has an atmosphere. That atmosphere is a giant stirring spoon. It mixes heat, spreads warmth, blurs the line between sunlight and shadow. Step into the shade on a summer day, and the shade is still warm, because the air has carried the sun's energy everywhere. The moon has no air, none, so shade on the moon is not just a darker spot, it is a different world. In direct sunlight on the lunar surface, the ground can reach about 250 degrees Fahrenheit, hot enough to boil water 3 times over. Step 6 inches into the shadow of a rock, and the temperature crashes to about minus 250 degrees Fahrenheit, a swing of 500 degrees across the length of your own foot. An astronaut standing in the sun on the moon experiences something no human on Earth ever has. The side of their suit facing the sun is being cooked, the side facing away is being frozen, and there is no air to carry heat from one to the other. This is confirmed by every Apollo mission. The spacesuits worn during the moonwalks were engineered to handle this exact problem. White on the outside, to bounce sunlight away, layered with insulation thick enough to slow the cold from reaching the skin, built with tubes of cool water woven through the inner layer to pull sweat and heat away from the body before the astronaut cooked inside his own armor. Buzz Aldrin said that stepping from sunlight into the shadow of the lunar module felt like walking into a freezer, even though he never touched a cold surface. The radiant heat just stopped. On the moon, sunlight is not a soft thing. It is a beam, hard and direct, with no air to soften it. When it stops, warmth stops. There is a darker version of this effect. In some parts of the moon, especially near the poles, there are craters where sunlight has never reached the floor, not in the past million years, not in the past billion. The sun sits so low on the horizon that the crater walls block it forever. The temperature inside those craters sits near minus 400 degrees Fahrenheit, colder than the surface of Pluto. Those craters matter to us, because inside them, water ice has been sitting untouched for billions of years. The moon is not dry. It is locked, frozen in places the sun cannot find. Future missions plan to mine that ice, to drink it, to split it into hydrogen and oxygen for rocket fuel. A single dark crater on the moon could hold enough water to supply a lunar base for a century. The coldest spots on our nearest neighbor may be the reason humans can live there. So the moon teaches a strange lesson. The cold is not your enemy. The cold is a vault. It preserves what sunlight would have burned away. It holds the keys to living on other worlds. And if the moon, a rock we have already walked on, can play this cruel trick with sunlight and shadow, imagine what happens deeper in the universe, where entire clouds of gas have grown colder than space itself. 5,000 light-years from Earth, there is a cloud of gas shaped like a bow tie. Astronomers named it the Boomerang Nebula, and inside that cloud, something is happening that should not be possible. It is colder than empty space. Confirmed measurements put the temperature of the Boomerang Nebula at about minus 458 degrees Fahrenheit. That is only half a degree above absolute zero. That is colder than the afterglow of the Big Bang, colder than the gap between galaxies, colder than anything else ever measured in the sky. Think about what that means. The background temperature of the universe is the floor, everything passive, everything still, should settle at that floor. The Boomerang Nebula broke through it. Something in that cloud is actively pulling heat out of itself faster than the universe can give it back. How? At the center of the nebula is a dying star. It is in the middle of one of the strangest death scenes in astronomy. Instead of exploding, it is breathing out. Massive streams of gas are rushing outward from its core at speeds over 300,000 miles per hour. That is roughly 10 times faster than the solar wind that leaves our Sunday. When gas expands, it cools. You feel this every time you use a can of compressed air. The can gets cold in your hand because the gas inside is rushing out and dropping in temperature. The Boomerang Nebula is that trick, scaled up to the size of a solar system. Gas is escaping so fast and expanding into such a huge volume that its temperature has been drained beneath the universe's natural floor. This is rare. Scientists believe the Boomerang Nebula is the only naturally occurring object we have ever found that is colder than the cosmic background. Everything else in the universe either sits at the background temperature or is warmer. The nebula is a cosmic anomaly. It will not stay that way. This is a confirmed theory. The dying star at the center will keep cooling and shedding gas for perhaps another 1,000 years. Eventually, the outflow will stop. The nebula will stop cooling. The background radiation will slowly warm it back up, returning it to the same floor as the rest of the universe. The coldest natural place we know of has an expiration date, but for now, it sits out there, glowing faintly, shining not with heat, but with the reflected light of its dying star. There is a strange beauty to this. The coldest object in the known universe was not built by a machine. It was not frozen by anything external. It cooled itself from the inside out by simply breathing out too hard. A star in its final breaths, making a grave colder than the grave of the cosmos. Scientists study the boomerang because it helps them understand what happens in the final acts of stars like our Sunday. One day, billions of years from now, our own sun will do something similar. It will swell, shed its outer layers, and leave behind a thinning cloud in its place. Whether that cloud will cool the way the boomerang has is still unknown. It may not. But it reveals a deeper truth. Cold is not always something that arrives. Sometimes, cold is something a dying object creates on the way out. Stars do not die quietly. They die in stages. And the last stage of a medium-sized star is one of the strangest things in the universe. Because the leftover cloud, the one that drifts for thousands of years after the star collapses, can end up colder than the vacuum that surrounds it. This is confirmed, and scientists are still working out every detail. Here is the scene. A star roughly the size of our sun has burned hydrogen in its core for about 10 billion years. The fuel is running low. The core shrinks and heats up. The outer layers swell outward, turning the star into a red giant, a bloated version of itself that can grow large enough to swallow nearby planets. Then, instead of exploding like a supernova, the star begins to shed. Slowly at first, layers of gas drift off into space, like steam rising from a pot. Then faster, the outer envelope peels away completely. What is left behind is the naked core, a white-hot ball about the size of Earth, called a white dwarf. The shed gas keeps moving outward. That gas is the nebula, the cloud of the dead star. Most of these clouds are warm at first, lit up by the white dwarf in the center. They glow in brilliant colors, pinks and greens, and electric blues. These are the images astronomers love to share, and they get photographed by every major telescope. Confirmed beauty, confirmed physics. But in rare cases, something different happens. The gas rushes out so violently, so fast, that it expands too quickly for the central star to warm it. The cloud outruns its own light source. As it expands, its temperature drops and drops and drops. Imagine blowing air out of your mouth onto your hand. Slow and steady, it feels warm. Now pucker your lips and blast a sharp breath. It feels cold. Same air, same temperature in your body. The only thing that changed was the speed of the escape. In the Boomerang Nebula, that same trick is happening on a scale no one on Earth can recreate. The gas is shooting outward at hundreds of thousands of miles per hour, expanding into a volume hundreds of times larger than our entire solar system. By the time that gas slows down, it has dumped almost all of its thermal energy into the void. This is how a dying star can leave behind something colder than the corpse of the Big Bang. It gets stranger, because the cloud can stay that cold for only a short time. The cosmic background is constantly feeding heat into every part of space, a thin whisper of radiation from every direction. That radiation warms the cold cloud back up, slowly, second by second. The coldness of the Boomerang Nebula is a racing collapse against a ticking clock, and that tells us something eerie about the universe. True cold, the kind that breaks through the floor set by the Big Bang, may only exist in brief moments. It is not a place, it is an event. When a star dies this way, it punches a cold hole in the universe. The hole closes, the warmth returns. The stars that come after never know the hole was there. And if stars can break the cold floor, planets can play their own tricks too, some of them in ways that make no sense at all. Mercury is the closest planet to the Sunday. It sits so near the fire that during the day, the surface temperature climbs to about 800 degrees Fahrenheit. That is hotter than a pizza oven. Lead would melt into puddles. Tin would flow like water. Now flip Mercury around. Walk to the side that faces away from the sun, and the temperature crashes to about minus 300 degrees Fahrenheit. A swing of more than 1,000 degrees on the same planet, across a distance you could drive in a day. This should not happen next to a star. And yet, this is confirmed by every probe that has ever visited Mercury, including NASA's Messenger spacecraft, which orbited the planet from 2011 to 2015. Here is why it happens. Mercury has no atmosphere, none to speak of. There is a thin haze of particles clinging to the surface, but nothing like Earth's sky. On our planet, the air acts like a blanket. When the sun sets, the atmosphere holds onto heat, releases it slowly, and keeps the night from becoming lethal. Even in the hottest desert, nighttime temperatures rarely drop below freezing because the air remembers the day. Mercury has no blanket. When the sun goes down, heat leaves instantly. It radiates straight out into the black, with nothing to hold it back. There is a second twist. Mercury rotates extremely slowly. A full day on Mercury, from one sunrise to the next, takes about 176 Earth days. That means when one side faces the sun, it faces it for months. And when the other side turns away, it stays in darkness for months. Heat cannot be stored. Cold cannot be chased away. Each hemisphere gets locked into its extreme. So the dark side of Mercury is not a night. It is a season. A long, merciless, frozen season of months-long shadow, right next to a star hot enough to boil rock. This gets even weirder in a specific place. Near the poles of Mercury, there are craters where the floor never sees sunlight at all. The angle is wrong. The sun barely rises above the horizon at those latitudes, and high crater walls block the light from ever reaching the bottom. Inside those permanent shadows, temperatures drop even further. We are talking about minus 360 degrees Fahrenheit, cold enough that water ice can exist there. On Mercury, the planet closest to the Sunday, the Messenger probe confirmed this in 2012. It found hydrogen signatures consistent with frozen water in the floors of polar craters that had never felt a single photon of sunlight. Think of it. Ice on Mercury, the cooking stone of the solar system, surviving for perhaps billions of years because it was hiding in the right shadow. This is one of the strangest facts in planetary science. The closer you are to the sun, the colder your darkest corners can get, because the contrast is so extreme. There is nowhere to soften the fall. Mercury teaches a brutal truth about the universe. Heat is not a general condition of being near a star. It is a local event. Step out of the light, and you step into a temperature that does not care what is blazing a few miles away. And in the far reaches of the solar system, some worlds have lost the light entirely. When a NASA probe called New Horizons raced past Pluto in 2015, it sent back photographs that shocked every scientist who saw them. Pluto was not a dead grey rock. It had mountains, valleys, cliffs, and a vast, smooth plain shaped like a heart. That plain, named Sputnik Planitia, turned out to be one of the most alien landscapes in the solar system. It is a frozen lake, not of water, of nitrogen. On Earth, nitrogen is the gas that makes up most of the air you are breathing right now. It floats, invisible, all around you. Your lungs fill with it every second of every day. It has never been liquid in your presence, and it certainly has never been solid. You would need to cool it to about minus 320 degrees Fahrenheit to even freeze it. Pluto is cold enough. In fact, Pluto is far colder than that. Surface temperatures on this tiny world hover between about minus 370 and minus 400 degrees Fahrenheit, low enough to freeze nitrogen solid and also to freeze methane and carbon monoxide. What on Earth would be air, on Pluto is rock. Sputnik Planitia is the size of Texas, maybe larger. It sits in a massive basin, and the nitrogen ice there is many miles deep, but it does not sit still. Here is where it gets eerie. The ice flows. Confirmed observations from New Horizons showed that the surface of this frozen lake moves slowly in huge, circular patterns. Warm nitrogen ice from deep below rises up, reaches the top, cools even further, and sinks back down on the edges. It is a convection pattern, the same as boiling water in a pot, but running at temperatures hundreds of degrees below anything on Earth. Each cell in this pattern is about 30 miles across. Each cycle takes about 500,000 years. You could stand on the surface of Sputnik Planitia for 1,000 generations and see no change with your eyes. But every few 100,000 years, the entire top layer of the frozen lake has been replaced by ice from deep within. This means Pluto is alive, in a geological sense. Not dead, not static. A living world with slow, cold currents pushing its frozen skin around like the slowest river ever discovered. There is another twist. The mountains that surround Sputnik Planitia are not made of nitrogen, they are made of water ice. Because at Pluto's temperature, water ice is as hard as granite, literally hard enough to form mountain ranges. Those peaks rise up over 10,000 feet, as tall as Sirius Mountains on Earth, and they are carved out of what Earth would call glacier. So picture the landscape. Jagged water ice cliffs, harder than stone, sliding between them a vast plain of nitrogen ice, shifting like a slow ocean, methane snow dusting the highlands. An atmosphere thinner than a whisper, freezing out of the sky in winter and rising back up in summer. Pluto is not just a frozen world. It is a world where the air itself has become the ground, where lakes are made of what you breathe, where stone is made of what you drink. And it is not the only place in the solar system where cold has rewritten the rules of chemistry. On one of Neptune's moons, the volcanoes erupt ice instead of lava. Voyager 2 flew past Triton in 1989. It was only a brief pass, a few hours of photos, a glimpse of a world no spacecraft has visited since, and what it showed left scientists stunned. The surface of Triton had dark streaks, miles long, shooting across pale pink ice, geysers, active ones, plumes of something rising several miles up into the thin atmosphere and then drifting sideways, pushed by faint winds. On a moon where the surface temperature sits around minus 390 degrees Fahrenheit. This is confirmed. Triton is the coldest active world ever observed in the solar system, and yet, somehow, it is erupting. The eruptions are not lava. Lava is molten rock, which requires temperatures in the thousands of degrees. Triton has nothing close to that kind of heat near the surface. What Triton has is something stranger: cryovolcanism. Cold volcanoes, eruptions of liquid or gaseous material that, on Earth, would be ice or air or something in between. The geysers seen by Voyager 2 appear to be jets of nitrogen gas, laced with dark dust. The gas likely comes from pockets of nitrogen ice beneath the surface, warmed just enough by weak sunlight or internal heat to turn from solid to gas. When it breaks through the crust, it bursts upward at high speeds, throwing dust particles miles into the sky. Think about that for a second. On Triton, a volcano is not fire, it is breath. The ground inhales a little warmth, then exhales a tower of gas through a crack. There is more. The surface of Triton has features that look suspiciously like frozen lava flows, except they are made of ice. Smooth patches, where something once flowed out of the ground, spread across a region, and then froze in place. Scientists suspect that under Triton's hard shell, there may be a layer of slushy, partly liquid water, warm enough to flow, cold enough that every other chemical around it is frozen solid. How does a world this far from the sun keep any heat at all? There are two candidate explanations, and both are theories, not confirmed facts. The first is tidal flexing. Triton orbits Neptune in a strange, backward direction, unlike any other large moon in the solar system. Most astronomers think Triton was not born near Neptune. They think it was a wandering object from the outer edge of the solar system that was captured by Neptune's gravity. The capture was violent. It bent Triton's orbit, stretched its insides, and heated its core through friction. That heating may still be slowly going on. The second is radioactive decay. The rocky core of Triton may contain enough uranium and other radioactive elements to keep its deep interior warm, trickling heat upward for billions of years. Just a thin trickle, enough to run a few geysers, but not enough to melt the surface. Either way, Triton proves something important. Cold does not mean dead. A world at almost 400 below zero can still burp, still flow, still erupt. It just does so in materials that would look, to us, like nothing but ice. If a moon this cold can have this much going on, the moons closer to the sun, warmer only by a little, must be even more alive. And some of them, hidden under shells of ice, may be hiding something we have been searching the universe for. Oceans. On the surface, they look dead. Two small moons, wrapped in pale ice, drifting around giant planets hundreds of millions of miles from the sunday. Temperatures on their surfaces drop to around minus 260 degrees Fahrenheit for Europa and around minus 330 degrees Fahrenheit for Enceladus. Underneath, both worlds are hiding a secret that has changed the search for life in the universe. They have oceans. Real, liquid, salty oceans of water, buried but alive. Europa is a moon of Jupiter, about the size of our own moon. Its surface is a cracked shell of water ice, smooth in some places, fractured in others. The cracks form long, dark lines that stretch across the entire world. Beneath that ice, confirmed by the Galileo probe in the late 1990s and supported by every observation since, there is a global ocean, not a lake, not a sea, an ocean that wraps around the entire moon. Scientists believe it is roughly 60 miles deep in places. That is deeper than any ocean on Earth, and it contains perhaps twice as much liquid water as every body of water on our planet combined. Enceladus is a moon of Saturn, much smaller than Europa. It is so small you could drive across it in a few hours if there were roads. But in 2005, the Cassini spacecraft photographed enormous plumes of water vapor shooting out from cracks near its south pole. Those plumes reached hundreds of miles into space. Cassini later flew through those plumes and tasted them, chemically speaking. The water contained salt, organic molecules, and hints of hydrothermal activity, which means hot water reacting with rock. On Earth, the places where hot water meets rock on the ocean floor are the places where life often thrives. Deep sea vents are crawling with creatures that have never seen the sunday. If the same setup exists on Enceladus, then somewhere, right now, there may be tiny living things feeding off the heat from hidden vents, under an ice crust that has hidden them from the universe. How do these oceans stay liquid? It is not the sunday. The sun is far too weak out there. At the distance of Jupiter, sunlight is about 1/25th as strong as on Earth. At Saturn, weaker still. The warmth comes from inside, and it comes from gravity. Both Europa and Enceladus are caught in the gravitational pull of their giant host planets. As they orbit, they are constantly squeezed and stretched by that pull. This flexing generates heat deep inside their cores, much like bending a paperclip back and forth warms the metal. That heat keeps the inner layers liquid, even while the outside freezes solid. The ice shell acts as a lid, a thick, white, insulating cap that keeps the warmth from leaking out. In some places, the shell may be only a few miles thick. In others, it could be over 20. But everywhere, it is enough to protect the ocean below from the killing cold of space. This is important for one reason. If life exists anywhere else in the solar system, it is probably in those oceans. And the next decade of space exploration is aimed squarely at them. NASA's Europa Clipper is already on its way to Jupiter, set to begin detailed studies of Europa's ice shell in 2030. Cold, it turns out, may be the one thing that made alien life possible. Metal is supposed to be strong. Bend it, and it flexes. Hit it, and it dents. Drop it, and it holds its shape. That is the world we know. At cryogenic temperatures, metal stops behaving that way. Cool steel to about -300 degrees Fahrenheit, and it changes. Not visibly, not in color. It still looks like steel, but inside, something has shifted. The atoms, which were vibrating freely and sliding past each other with ease, have slowed down. The metal has become stiff, rigid, brittle. Tap it hard, and it can crack. Stress it in the wrong spot, and it shatters like glass. This is not a theory. This is an engineering nightmare that has killed projects, grounded spacecraft, and cost lives. The most famous example is the Titanic, although that was a shipwreck, not a space mission. The steel of the Titanic's hull became brittle in the freezing North Atlantic water. When the iceberg struck, the hull plates cracked along their seams, rather than bending inward. Analysis of recovered hull steel decades later confirmed it. The metal was too cold to flex. It snapped. In space, this problem is much worse, because parts of spacecraft can reach temperatures far below what the Titanic ever experienced. On the shaded side of a satellite, metal may sit at -250 degrees. Inside the fuel tanks that hold liquid hydrogen, temperatures drop to nearly -425 degrees Fahrenheit, barely above absolute zero. At those temperatures, ordinary steel is useless. It is too brittle to hold pressure. One good bump, and the tank would burst. So spacecraft designers have to choose special alloys, stainless steel, aluminum lithium, certain titanium blends. These metals have been engineered to keep some of their flexibility, even in the deep cold. They are more expensive, they are harder to shape, but they do not shatter at the slightest shock. Even these special metals have limits. Engineers have to test every single part at temperature before it flies. They cool samples down in specialized chambers, hit them with hammers, twist them, freeze them for days, and look for the slightest sign of cracking. If a part fails, the entire mission design can change. There is a second problem. Metal shrinks when it cools. A steel beam, 100 feet long, will shrink by a few fractions of an inch if you cool it deeply. That sounds small, until you realize a rocket stage is thousands of parts fitted tightly together. If one shrinks more than another, seals break, bolts loosen, fuel leaks where it should not. Pipes that were perfectly aligned at room temperature pop apart when the cold hits. This actually happened to the Space Shuttle program. In 1986, the Challenger disaster was partly caused by rubber O-rings that lost flexibility in the cold weather before launch. The O-rings were not supposed to freeze. The morning was unusually chilly. The rubber hardened just enough to fail. 7 astronauts died because a material had become too stiff to do its job. This is why cold is taken seriously by every space agency on Earth. It is not just uncomfortable. It is a quiet, patient destroyer. It turns ductile metal into pottery. It shrinks perfect fits into leaking failures. It punishes any engineer who assumes warmth is free. If cold can crack steel, imagine what it can do to a human body in an environment where the usual rules of heat do not apply. On Earth, your body sheds heat all day without you thinking about it. You lean against a cool chair, and the chair pulls warmth out of your back. You stand in a breeze, and the breeze carries heat off your skin. You breathe out, and warm air leaves your lungs. These are everyday, quiet ways of cooling. In space, none of them work. There is no chair, no breeze, no air to breathe out. The 3 main ways the human body transfers heat, conduction, convection, and respiration, all require matter. They all require molecules to carry the energy away. In a vacuum, the molecules are gone. So how does your body cool in space? There is only one method left: radiation. Everything warm gives off radiation. Your hand, right now, is glowing in infrared light, invisible to your eyes, but very real. That glow is energy leaving your body and racing out into the world. On Earth, it is a small part of your total heat loss. In space, it is the only part, and it is slow. Your skin, at body temperature, radiates heat at a rate of about 100 watts. That is roughly the output of an old light bulb. It means that, in a vacuum, without a suit, a naked human body would lose its warmth at about the same rate a 100-watt bulb loses its energy to the room. Sounds fast. It is not. The human body holds a lot of thermal energy. It would take many hours, not seconds, for radiation alone to drop your body temperature to anywhere close to freezing. This is why so many movies get it wrong. The image of a person instantly turning into an ice statue the moment they step into space is a myth. The truth is far creepier. You would still be warm when you died, because you would suffocate long before you froze. But here is where it gets worse. That slow radiation problem works in reverse too. If you are inside a spacecraft, and the spacecraft is sitting in direct sunlight, heat cannot escape easily. The outside of the craft radiates heat, but only as fast as its surface allows. Inside, the air heats up, the walls heat up, the equipment heats up. This is a real engineering nightmare. In low Earth orbit, spacecraft often swing from sunlight to shadow and back every 90 minutes. When they are in the sun, everything tries to overheat. When they are in the shadow, everything tries to freeze. The only way to manage the swing is with radiator panels, giant wings of metal that face away from the sun and dump heat out into space as infrared light. The International Space Station has these radiators. They are enormous. They are the only reason the station does not cook itself from the inside. They are also the only reason it does not freeze during orbital night. So in space, temperature is not something you feel. It is something you engineer. Warmth is a resource you manage, second by second. Too little, and your equipment shatters. Too much, and your crew boils inside their own walls. The vacuum does not attack you with cold. It attacks you by removing every normal way of trading heat with your surroundings. And some of the coldest places in our own backyard exist for the exact same reason. Places where sunlight never arrives, and the heat never comes to balance it out. Stand in the sunlight on the moon, and the ground beneath your boots is hotter than boiling water. Step behind a rock, and the temperature plunges to levels that would freeze nitrogen out of the sky. That is the power of a single shadow on the moon. On Earth, a rock's shadow is just a cool patch. You might rest in it on a hot day. The air inside it is a few degrees cooler than the air in the sun. On the moon, with no air at all, the shadow is not a small cooling. It is a cliff. A sudden drop of hundreds of degrees from one side of the rock to the other. Scientists have measured this. In the Apollo missions and in later orbital surveys, instruments have tracked surface temperatures square meter by square meter. The results are astonishing. Directly beside a sunlit boulder, the ground reads at around 250 degrees Fahrenheit. 6 inches into the shadow cast by that same boulder, the reading drops to around -170. Why such an extreme change? On Earth, sunlight heats the air, and the air spreads the heat. Even in shade, warm air blows in and raises the temperature. On the moon, sunlight heats only what it touches. There is no air to circulate. There is no ground conduction either, because the dusty lunar surface is a terrible conductor of heat. The warmth stops at the edge of the light. In the shade, temperature drops as fast as radiation can carry it off, and without a blanket of air, that is fast. Within minutes of losing sunlight, a patch of lunar dust has given up most of its warmth. This becomes extreme inside certain lunar craters. Near the moon's poles, the sun never rises high. It crawls along the horizon, low and flat, the way it does in winter at the Earth's poles. In some craters, the angle is so shallow that the walls always block the light from reaching the floor. Those crater floors have not seen sunlight for billions of years. NASA's Lunar Reconnaissance Orbiter mapped these craters in detail, starting in 2009. It found temperatures inside some of them below minus 400 degrees Fahrenheit. That is colder than the surface of Pluto, colder than almost any natural surface in the solar system. This has a practical consequence that could shape the future of space travel. Inside those permanent shadows, water has been surviving as ice for billions of years. Comets crashed into the moon long ago, released water vapor, and the vapor that drifted into those cold traps froze instantly and never left. Confirmed detections by the L-Cross mission in 2009 found exactly this. When a probe deliberately crashed into one of those shaded craters, it kicked up a plume containing water ice, real water on the moon, in a place where the temperature is colder than most of our solar system. That ice could become rocket fuel. Split water into hydrogen and oxygen, and you have the ingredients for rocket propulsion. A permanent lunar base could be built near these craters, mining water from shadows that the sun has never touched. The coldest corners of the moon, the places most hostile to life, may be the very reason life can someday spread off Earth. Cold is not always the enemy. Sometimes it is the savior. There are places on the moon where the sun has never shined. Not ever. Not once in 4.5 billion years. These are the permanently shadowed regions, or PSRs, and most of them lie near the north and south poles of the moon. From orbit, they look like ordinary craters, circular bowls scooped into the lunar surface by ancient impacts. Their rims stand tall against the sky. Their floors sit hidden beneath those rims. At the bottom of deep pits, the trick is the angle of the sunday. At the poles of the moon, sunlight arrives almost sideways, grazing the horizon. It strikes the rim of the crater, but the rim casts a shadow that completely covers the floor. Because the moon's rotation is almost perfectly upright, unlike Earth's tilted axis, that shadow never shifts with seasons. Year after year, the shadow stays. Century after century, eon after eon. No sunlight, no warmth, no change. The temperature inside these craters, confirmed by orbital measurements, can fall below minus 410 degrees Fahrenheit, only a few dozen degrees above absolute zero, the coldest point physics allows. What makes these places so extraordinary is that they are time capsules. Anything that lands inside one of these craters and does not bounce out becomes trapped. There is no sunlight to warm it, no wind to blow it away, no water to dissolve it. It simply sits, frozen, for as long as the moon lives. Over billions of years, comets and meteorites have crashed into the moon. Many of them contained water, ammonia, methane, and other icy materials. When those materials splashed onto the warm, sunlit parts of the lunar surface, they evaporated into space almost immediately. But some of them drifted, as thin vapors, across the moon before the sun could destroy them. A small fraction of that vapor wandered into the polar shadows. Once inside, the vapor froze, and it stayed. We believe, based on orbital measurements, that billions of gallons of water ice may be locked in these craters right now. Enough water to support a permanent human base, maybe enough to support a city. Every major space agency, including NASA, China's CNSA, and private ventures, is planning missions that aim directly at these dark, frozen regions. The Artemis program is one of them. It aims to put astronauts on the lunar South Pole within this decade, partly because of this ice. Future astronauts will not be visiting for flags and photos. They will be visiting for water. There is also a stranger possibility. Because these craters have been sealed in the same state for billions of years, they may contain more than ice. They may contain records, chemical traces of every comet and asteroid that struck the inner solar system across the entire history of life on Earth. If we could sample that ice, we might be reading a history of our own origins, preserved in a frozen vault on a dead grey moon. Life itself may have delivered some of its early ingredients to Earth in just this way. Water, organic molecules, maybe even proteins, carried by comets through deep space. Some of those same comets likely hit the moon as well. What evaporated on Earth may still be locked in these shadows. Sunlight gives us life, but shadow, in the right place, preserves it. And that preservation spreads farther than the moon. It stretches out to the rings of Saturn, frozen for longer than Earth has existed. Saturn's rings are one of the most recognizable sights in the solar system. A giant planet, striped in pale gold, wrapped in a flat disk of sparkling light. Even a backyard telescope can show them. What most people do not know is what those rings are actually made of. They are made of ice, almost pure water ice. Tiny chunks, most of them smaller than a marble, some the size of cars, a few as big as mountains. Trillions of them, orbiting Saturn in a band thousands of miles wide, but only a few dozen feet thick in most places. This is confirmed by decades of observations, including the Cassini mission that ended in 2017. So here is the puzzle. How can a disk made of ice, sitting in direct sunlight, exist for billions of years without melting? Water ice on Earth evaporates even at freezing temperatures. Given enough time, the ice cubes in your freezer shrink over the months. They sublimate, turning from solid straight into gas. Eventually, they vanish. Yet Saturn's rings have been there for a long, long time. Estimates suggest they formed at least several 100 million years ago, and possibly several billion. They should have evaporated away. Why have they not? The answer is distance. Saturn is about 9 times farther from the Sun than Earth is. That means sunlight at Saturn is about 80 times weaker than sunlight at Earth. A surface that would warm in seconds on our planet barely warms at all out there. The ring particles sit at roughly minus 300 degrees Fahrenheit. At that temperature, water ice is stable. It can sit in a vacuum for geologic ages without losing noticeable mass. It is no longer a material that melts or evaporates on human timescales. It behaves more like stone than like ice. A floating gravel bed of sparkling frozen water. There is a second protection. Each ring particle is constantly being cleaned. The chunks collide with each other gently as they orbit. New surfaces get exposed. Old surfaces get buried. This is why the rings look so bright. Their outermost layer is freshly smashed ice, reflecting sunlight like a field of broken mirrors. There is also a slow process of destruction. Micrometeorites hit the rings and slowly contaminate them with dark dust. Gravity from Saturn's moons pulls the rings in different directions, creating waves and spirals. The rings are thinning over hundreds of millions of years. Eventually, they may disappear entirely. That is a confirmed theory based on Cassini data. The rings may not last another 100 million years. For now, they persist. A giant, quiet, frozen sculpture around a distant world, staying cold because the sun is simply too far away to reach them. There is something to think about here. The rings of Saturn, as huge and glorious as they look, are made of an amount of ice roughly equal to a very small moon. If you piled every single particle into one object, the result would be tiny compared to Saturn itself. Their size in the sky is an illusion of spread, of width, not mass. And the same logic, the idea that distance from a star is the only real defense against heat, applies far beyond Saturn. It extends out to a planet so tipped that it turns its face away from the sun for decades at a time, and freezes an entire hemisphere in the process. Every planet in our solar system spins. Every one of them tilts a little as it spins, which is why Earth has seasons. Our tilt is a modest 23 degrees, enough to give us summer and winter, but nothing extreme. Uranus is not modest. Uranus is tipped 98 degrees. This is not a spin. This is a roll. Uranus lies on its side as it orbits the Sunday. Its north pole points directly at the sun for part of the year, and directly away for another part. Imagine a top that got knocked over and then kept spinning while lying on its side. That is Uranus. This tilt creates the most extreme seasons in the solar system. Uranus takes about 84 Earth years to orbit the Sunday. Because of its extreme tilt, each pole spends about 42 years in continuous sunlight and then about 42 years in continuous darkness. Every human being alive today will live through only 1 or 2 lunar seasons on Uranus. Now consider what that means. During its long winter, a full hemisphere of Uranus plunges into 4 decades of uninterrupted night, no sunrise, no dawn, 42 Earth years of unbroken darkness. The temperature of Uranus already hovers around minus 350 degrees Fahrenheit at the cloud tops. making it the coldest planet in the solar system on average, even colder than Neptune, which is farther from the Sun. That average is only possible because Uranus, unlike other giants, emits almost no internal heat. It is a cold, quiet giant, confirmed by the Voyager 2 flyby in 1986 and by decades of telescope observations since. In the hemisphere currently buried in darkness, the temperature can drop even lower than the average. The cloud tops facing away from the sun receive essentially zero warmth from sunlight for decades on end. Only the slow heat escape from the planet's interior and the faint warmth of the cosmic background keep things going at all. Why is Uranus tipped this way? Scientists suspect a catastrophic collision. Very early in the history of the solar system, perhaps 4 billion years ago, something huge slammed into Uranus and knocked it over. The impact was so violent, it changed the entire spin axis of the planet. That is a theory, not a confirmed fact, but it is the leading explanation. There is another oddity. Because the planet is tipped, its magnetic field is also tilted at a strange angle, about 60 degrees from its spin axis, and the magnetic field is not centered in the planet. It is offset toward one side, as if someone inside was holding a bar magnet crookedly. No one fully understands why. It is a confirmed observation and an open mystery. Uranus also has faint rings, much darker than Saturn's. They are made of darker material, more like coal than ice. But they share the same property of staying cold because Uranus receives so little sunlight. The rings wrap around the tipped planet at the same strange angle as its axis, meaning they appear vertical from our point of view, not horizontal like Saturn's. The whole system of Uranus is a reminder that the universe plays rough. Worlds can be pushed, knocked, frozen, and reshaped by single events that happened before the first cells formed on Earth. And in places far beyond Uranus, the cold gets even deeper. It reaches a level where sunlight is no longer relevant at all. Leave the solar system behind. Pass the orbit of Pluto. Keep going. Cross the bubble of the sun's influence and enter the space between the stars. Out there, everything changes. The sun is just another bright dot, a yellow pinprick, no more powerful than Sirius or Alpha Centauri. There is no longer any meaningful warmth coming from our local star. The temperature of any object drifting in interstellar space depends almost entirely on the combined faint glow of every star in the galaxy and on the cosmic background radiation. That combined heat is tiny. Out there, a floating rock settles at about -440 degrees Fahrenheit. That is the coldest normal temperature you will find in nature, outside of special anomalies like the Boomerang Nebula. This cold is beyond anything humans can produce with ordinary technology. Your best commercial freezer reaches about -20 degrees Fahrenheit. A laboratory ultra-cold freezer can hit -150. Liquid nitrogen takes you to about -320. Liquid helium about -450. To match interstellar space, you need advanced cryogenic systems that use special refrigeration tricks, and you have to maintain them constantly. Any leak of warmth, any contact with a warmer object, and the temperature jumps back up. On Earth, cold, this deep, is a continuous fight. In interstellar space, it is the resting state. What does that mean for matter? At these temperatures, most normal chemistry stops. Reactions that need warmth to proceed simply cannot happen. Molecules freeze solid, gases condense into ices. Even hydrogen, the most stubborn of all elements, can begin to stick to surfaces instead of flying off them. Interstellar space is a place where the universe's normal cleanup processes run at a crawl. This is why interstellar dust is so strange. Tiny grains floating between the stars, a few times bigger than molecules themselves, get covered in icy coatings over millions of years. Water, carbon dioxide, methane, and more complex organic chemicals build up layer by layer, like frost on a car window, except they take thousands of centuries to form. Some of those dust grains end up in the clouds where new stars and planets are born. The ice coatings survive the early stages of collapse. They carry complex chemistry right into the new solar system, where they may become part of the raw material for life. Every drop of water on Earth may trace its origin, in part, back to the icy grains of interstellar space. So this deep cold is not empty. It is creative. It is slow. It builds things that warmer environments destroy, and it does it patiently, over timescales longer than civilizations. There is one more fact about interstellar space that should quietly unsettle you. A spacecraft sent there, like Voyager 1, which crossed into interstellar space in 2012, is slowly cooling down toward these temperatures. Its electronics still produce a trickle of heat, but that trickle is fading year by year. Eventually, Voyager 1 will drop to nearly the same temperature as the dust and gas around it. It will no longer be a spacecraft. It will be another cold object in the great gap between suns. And beyond even that, if you keep going, you pass out of the galaxy itself. There, in the spaces between galaxies, cold takes on a meaning shaped not by stars, but by the oldest light in existence. There is a kind of light filling every corner of the universe right now. It passes through you every second. It passes through the room you are in. It passes through the Earth itself, through the sun, through every star in every galaxy. You cannot see it with your eyes. You cannot feel it with your skin. But it is there, and it is older than any star. It is called the cosmic microwave background, and it is the reason nothing in the natural universe can fall below a certain temperature. Here is the story. About 13.8 billion years ago, the universe began in a state of unimaginable heat. Not a single star existed, not a single atom either, because it was too hot for atoms to hold together. The entire cosmos was a thick fog of particles and radiation, trillions of degrees, a roaring ball of energy expanding outward in every direction. For about 380,000 years, the universe stayed opaque. Light could not travel freely. The fog was too dense. Then, at last, the universe expanded enough and cooled enough for atoms to form. The fog cleared. Light was released in all directions at once. That light has been traveling ever since. Over billions of years, as the universe kept expanding, the light stretched. Its wavelengths grew longer and longer. What was once visible fire became infrared, then microwaves. Today, that ancient light is the cosmic microwave background, a faint hum of radiation glowing at about 3 degrees above absolute zero. It fills everything. It comes from every direction. It is nearly the same temperature everywhere in the sky, with only tiny variations smaller than 1 part in 100,000. Those variations were the seeds of every galaxy, every cluster, every structure we see today. This background sets a floor on cold. Any ordinary object in the universe, sitting still, doing nothing, will eventually come to match this temperature. It cannot drop below it, because the background radiation is constantly pouring into the object from every direction. It is a universal warming blanket, too weak to feel, too wide to escape. That is why the coldest places in the universe are so rare, without some active process cooling them, like the runaway expansion of the Boomerang Nebula. Nothing in nature can outrun this flaw. But here is what makes the cosmic microwave background haunting. It is fading. As the universe continues to expand, the background keeps stretching thinner. Its temperature is dropping, infinitely slowly, but continuously. Right now, it sits at about 2.7 degrees above absolute zero. In 1 trillion years, it will be a small fraction of that. In much longer times, it will approach absolute zero itself. This means the universe is getting colder, not warmer. The natural direction of the cosmos is downward in temperature, toward a dark, frozen future where even the faint glow of creation has stretched into nothing. Scientists can detect this background with simple antennas. Your old television, back in the days of analog static, was picking it up. A small percentage of the snowy hiss on an untuned channel was ancient light from the Big Bang. You were watching the birth of the universe without knowing it. That faint hum is the floor, the foundation, the oldest sound in existence. And every degree of warmth we ever feel, on Earth or anywhere else, is built on top of it. Imagine the sun vanishes, gone, not exploding, not dying, simply erased in an instant while you are asleep. This is a thought experiment, not a real possibility. But scientists have run the numbers carefully, and the results reveal just how much warmth our star pumps into Earth every second. Minute 0. The sun disappears. You notice nothing. Sunlight takes about 8 minutes to reach Earth. So for the first 8 minutes, the sky looks normal. Minute 8, the sky goes dark. Not slowly, instantly. If it was daytime where you live, the world blinks to black. If it was night, the stars stay where they are, but the horizon never brightens again. The faint glow of twilight, which lingers for hours after sunset in a normal evening, is gone. Hour 1. The earth is still warm. The air, the oceans, the ground, all still hold the day's heat. Temperatures have barely moved. If you are inside with the heat on, nothing yet feels different. Hour 6. The air has cooled noticeably. Clear skies are a problem. Without clouds, heat escapes faster. In desert regions, thermometers may already show temperatures below freezing. In humid areas, clouds hold on to heat a little longer. Day 1. A full day has passed without sunlight. The average global temperature has dropped by roughly 10 degrees Fahrenheit. Plants have already begun to die. Photosynthesis, the process every green leaf relies on, stopped the moment the sun vanished. Crops in the field are freezing. Leaves are drooping. Week 1. The planet's surface averages below freezing in most regions. Oceans are still mostly liquid because they hold massive amounts of heat, but the surface of lakes and rivers is icing over. Storms rage across the planet as warm ocean air rises into a frozen atmosphere. The wind is screaming. Month 1. Surface temperatures have fallen to about minus 20 degrees Fahrenheit on average. Most of the world's land is covered in snow. Fresh water is nearly all ice. Only the oceans are still warm enough to support life in shallow waters. Deep sea vents continue their steady work, supporting tube worms and microbes that never needed the sun in the first place. Year 1. Temperatures across continents have crashed to around minus 100 degrees Fahrenheit. The atmosphere itself is starting to freeze in places. Carbon dioxide is condensing and falling as dry ice snow near the poles. Oxygen itself is getting close to liquefaction in the coldest spots. Year 10. The oceans have frozen solid down to a depth of more than 1,000 feet. Only in the deepest trenches, near hydrothermal vents, does liquid water survive. Earth has become a frozen ball. From space, the planet looks white and lifeless, like Europa or Enceladus. Eventually, over thousands of years, the oceans would freeze completely. The atmosphere would collapse. Earth would become a cold, dead, grey world, drifting through space like any other ancient rock. The lesson here is simple. The sun is not a background detail. It is the engine of every warm thing on Earth. The soil, the water, the air, the life inside you. All of it runs on sunlight, minute by minute, day by day. And sunlight is not guaranteed. It came from a star that was born. One day, that star will die. That future is far away, but it is real. And long before it happens, Earth itself has already come close to freezing into oblivion once before. About 700 million years ago, long before dinosaurs, long before fish, long before almost anything you would recognize as life, our planet froze over. Not partly, not at the poles only. The entire surface, from the equator to the poles, Earth became a ball of ice. This is known as snowball Earth, and it is a confirmed event supported by rock layers found on every continent. Glacial deposits from this period sit in places that were once tropical, right on the ancient equator. Ice reached the warmest parts of our world. The temperature dropped to an average well below freezing across the globe. Oceans iced over down to thousands of feet. Continents were buried under glaciers, miles thick. The planet looked, from space, almost exactly like Europa or Enceladus do today. A frozen white marble, lit faintly by a sun that seemed to have given up. How did this happen? Scientists are still working out the details, but there are strong theories. The first piece is the sun itself. 700 million years ago, the sun was about 6% weaker than it is now. Stars like ours slowly brighten over billions of years, so the ancient sun could not push as much warmth to Earth as the modern one does. The planet was already riding closer to the edge of ice. The second piece is rock weathering. Over millions of years, huge volcanic outpourings created vast plains of fresh volcanic rock. When rain falls on those rocks, chemical reactions pull carbon dioxide out of the air and lock it into the stone. Carbon dioxide is a greenhouse gas. It traps heat. When too much of it gets pulled out of the atmosphere, the planet cools. As it cooled, ice spread. And here is the ugly feedback. Ice is white. White reflects sunlight. The more ice grew, the more sunlight bounced straight back into space. And the colder the planet got. Cooler meant more ice. More ice meant cooler still. The cycle ran away. Eventually, the entire surface was frozen. Life survived, barely. Simple organisms hid under the ice, in pockets near volcanic vents, or in small cracks where liquid water still existed. Most complex life at that time was single-celled, so it could endure in places where a frog or fish could not. But the evolutionary timeline paused. For millions of years, Earth held its breath. What pulled the planet out of this deep freeze? Volcanoes. Even under the ice, volcanoes kept erupting. They kept releasing carbon dioxide. And because the ice was covering the ground, the carbon dioxide could not be pulled back into rock as easily. It built up in the atmosphere, and built up, and built up. Eventually, the greenhouse effect grew so strong that it overpowered the reflective ice. The planet began to warm. The ice melted, first at the equator, then spreading outward. The melt was violent. Floods swept across continents. The oceans absorbed carbon dioxide and became slightly acidic. Life exploded out of its hiding places in a wave of change so profound that it may have triggered the Cambrian explosion, the event that gave rise to almost every major animal group alive today. The lesson from Snowball Earth is humbling. Our planet is not immune to deep cold. It has experienced it. It has survived it. But the survival was close, and the recovery was violent. Earth is a warm world only by the thinnest of margins. Titan is the largest moon of Saturn, and the second largest moon in the solar system, after Jupiter's Ganymede. It is bigger than the planet Mercury. It has a thick atmosphere, denser than Earth's, made mostly of nitrogen with a dash of methane. It is also, hands down, the most Earth-like world in the entire solar system. Not because it is warm, not because it has water, but because it has weather. Real weather, clouds, rain, rivers, lakes, seas, seasons, fog, all of it made from methane and ethane instead of water. Titan's surface temperature sits at around -290 degrees Fahrenheit. At that temperature, water is rock. It is as hard as granite. You could build skyscrapers out of it. But methane, the gas that powers stoves on Earth, behaves on Titan the way water behaves here. It can exist as solid, liquid, or gas. It rains methane on Titan. The droplets fall slowly because the gravity is lower and the atmosphere is thicker. You would see them drift down like slow snow. The rain pools into streams. The streams run into lakes. The lakes connect to seas that cover thousands of square miles. Some of those seas, confirmed by the Cassini spacecraft and its lander probe Huygens, are absolutely massive. The largest, called Kraken Mare, is roughly the size of the Caspian Sea on Earth. It is full of liquid methane and ethane, lapping gently against shores of frozen water ice, with hydrocarbon fog drifting over the surface. Titan has a complete hydrological cycle. Methane evaporates from the seas. It rises into clouds. The clouds move with the winds. The clouds produce rain. The rain carves rivers. The rivers flow back to the seas, all of it powered by sunlight weaker than a desk lamp, 1 billion miles from the Sunday. Huygens, which landed on Titan in 2005, photographed the surface up close. The pictures showed a flat, rocky plain covered in rounded pebbles. Those pebbles were not stone. They were ice, shaped and smoothed by liquid methane the way stones on Earth are shaped by rivers. The landscape looked familiar, like a dry riverbed in the American Southwest, except none of it was made of what you would expect. The atmosphere above is orange, hazy, and thick. Sunlight struggles through it. A noonday on Titan would feel like a smoky sunset on Earth, dim, yellow, eerie. Yet this alien world has a strange beauty. Wind blows across its seas. Waves rise and fall, though gently because gravity is low. Snowfalls of hydrocarbons drift down onto the land. In some ways, standing on Titan's shore would feel like standing on Earth, if Earth had been chilled past the point of reason and had a different chemistry set. There is a chance, a real chance, that life could exist in this alien chemistry. Not water-based life, but something different. Scientists have proposed that microbes could theoretically use liquid methane as their solvent instead of water. If they do, they would work very slowly, because chemistry runs sluggishly in such cold. But given enough time, life might still take hold. Titan is a preview of just how diverse cold can be. It is not always a sterile void. Sometimes it is a new kind of home, running on a fuel we would never have guessed. And farther out still, the cold makes other worlds reign something even stranger. Uranus and Neptune are called the ice giants, not because they are made of ice, as you know it, but because their bulk is a soup of water, ammonia, and methane, under so much pressure that these materials behave in ways that have no match on Earth. At the top of both planets, visible from outside, there are cloud layers of methane. These give Neptune its deep blue color, and Uranus a paler cyan. Winds scream across their upper atmospheres at over 1,000 miles per hour, the fastest winds in the solar system. The upper air temperatures sit around -350 degrees Fahrenheit. As you sink below those cloud tops, the pressure rises fast. The temperature rises too, because the interior of each planet is heated by slow gravitational compression. By the time you are a few thousand miles down, the pressure and heat are unlike anything on Earth. This is where the diamond rain comes in. Deep inside Uranus and Neptune, the methane molecules start to break apart. Methane is made of carbon and hydrogen. When you crush it hard enough, under enough heat, the carbon separates out. The loose carbon atoms then clump together. Under even more pressure, they crystallize into diamond. Those diamonds would then fall, slowly, downward, through the mushy, liquid-like interior of the planet. They would rain, hailstorms of precious stones, sinking through layers of exotic fluid, heading toward a core deep inside the ice giant. This is a theory, supported by laboratory experiments. In recent years, scientists at high-pressure research labs in Germany and the United States have managed to recreate these conditions briefly. They fired powerful lasers at compressed hydrocarbons, simulating the deep interior of an ice giant for a few billionths of a second, and they detected the formation of real diamond crystals in the collapse. This was confirmed in experiments published over the last decade. It is one of the most striking findings in planetary science. Worlds we thought of as empty blue marbles are, deep inside, raining jewels. There is more. The middle layers of Uranus and Neptune may contain a superheated, electrically conductive form of water called ionic water. This is a state of matter where hydrogen and oxygen atoms break apart and flow like a strange liquid metal. This ionic ocean is what may generate the weirdly tilted magnetic fields of both planets. The one inside Uranus is tipped 60 degrees from the spin axis. The one on Neptune is tipped 47 degrees. Neither is explained by normal planetary models, but ionic water inside could cause exactly this kind of magnetic disorder. And yet, despite all this interior action, the outside of these worlds is brutally cold. The cloud tops are frozen. The upper atmosphere is frozen. The coldest temperature ever recorded on the tops of Uranus sits around -371 degrees Fahrenheit, colder than anywhere else on a solid or gaseous body in our solar system. Both Uranus and Neptune have rings, faint, dark rings that have their own storms of frozen dust. They have moons made of ice, some with suspected subsurface oceans. They are entire systems, frozen on the outside, churning on the inside, barely explored. Only one spacecraft, Voyager 2, has ever visited them, and only briefly, in the 1980s. Everything we know about diamond rain and ionic oceans comes from lab experiments and distant telescope measurements. These worlds are, in many ways, still mysteries. Cold hides what warmth would reveal, and the colder the world, the better the hiding place. Far beyond the planets, far beyond Pluto, far beyond anything a spacecraft has ever reached, there is a ghostly shell of frozen objects surrounding our entire solar system. It is called the Oort cloud. No one has ever seen it directly, it is too far, and its members are too small and too dim. But its existence is strongly supported by the behavior of long-period comets, which plunge into the inner solar system from random directions, carrying signatures of a cold, distant origin. The Oort cloud is thought to extend from about 2,000 times the distance between Earth and the Sun, all the way out to perhaps 100,000 times that distance. At its outer edge, it may reach a quarter of the way to the nearest star. The Sun's gravity barely holds on out there. Any small object drifting in the cloud can be nudged by the gravity of passing stars, sometimes tossed inward toward the inner solar system, sometimes kicked out into interstellar space forever. The objects inside it are comets, trillions of them. Each one is a dirty ball of ice, dust, and ancient frozen chemistry. Most are a mile or two across, though some are much bigger. They have been sitting out there, quietly, for about 4.5 billion years, ever since the solar system formed. Out at that distance, the Sun is a bright star, but nothing more. Sunlight carries almost no warmth. The temperature of an Oort cloud comet hovers around -440 degrees Fahrenheit, nearly the temperature of interstellar space itself. At that temperature, almost nothing happens. No chemistry, no change. The ice of an Oort cloud comet is the same ice it was when the solar system was born. This makes comets like living fossils. When one gets nudged inward by a passing star or galactic tide, it begins the long fall toward the Sunday. Over tens of thousands, or even millions of years, it accelerates down the gravitational slope, building up speed. Eventually, it enters the inner solar system. Sunlight grows stronger. The surface ice starts to warm. Gases vent outward. A glowing coma forms. A tail streams behind the nucleus. And scientists watching from Earth get to study something that has been preserved in cold storage for billions of years. This is how we know what the early solar system was made of. Comets carry the original recipe. Water, carbon dioxide, methane, ammonia, complex organic molecules, even simple amino acids have been detected in cometary material. The chemistry we find in modern comets is a snapshot of conditions that existed before Earth was even warm. Some scientists believe that comets delivered some of this material to early Earth, that much of our water may have come from comet impacts in the early solar system, that some of the ingredients for life may have arrived on frozen wings from the outer dark. This is a theory, not a fact, but it is consistent with the chemistry we find. The Oort cloud is a reminder that deep cold is not always destructive. Sometimes it is the only place where certain things can survive. Without it, the ancient chemistry of the solar system would have been cooked off long ago. And cold, truly deep cold, is not just a preserver, it is a shelter. It is a museum without curators. And for some objects, it is a permanent home, including worlds that wander alone, without any sun at all. Every planet you have ever heard of is tied to a star. Earth orbits the Sunday, Mars orbits the Sunday, even Pluto and distant objects beyond it belong to our star. Exoplanets, the ones discovered around other suns, are all gravitationally linked to some kind of sun somewhere. But there is another kind of planet, one that does not orbit any star at all, a rogue planet, drifting alone through the dark, with no sunrise, no sunset, no seasons, no light. Confirmed detections of rogue planets began in the 2010s using gravitational microlensing. When a rogue planet passes in front of a distant star, its gravity briefly bends the star's light, creating a small flicker that telescopes can detect. From these flickers, astronomers have estimated that the number of rogue planets in the Milky Way may actually exceed the number of stars. There could be hundreds of billions of them, perhaps trillions, drifting between the stars, never warmed by any sun. How does a planet end up like this? There are a couple of likely pathways. Some rogue planets probably formed around stars normally, then got ejected early in their solar system's history. A close encounter with a bigger planet or a passing star can give a small world enough of a shove to break free of its sun forever. Once ejected, it keeps moving, forever, in whatever direction it was last kicked. Others may have formed on their own, In some dense clouds of gas, small pockets can collapse into planet-sized objects without ever gathering enough material to become a star. These lonely objects are born as rogues. They have never belonged to anyone. The temperature of a rogue planet depends almost entirely on its own internal heat. Without a sun, it cannot be warmed from outside. The only heat it has is whatever it held onto from its formation, or whatever is generated by radioactive decay deep in its core. This makes their surfaces extremely cold. A rogue planet the size of Earth might have a surface temperature of around -400 degrees Fahrenheit, held up only by a faint trickle of geothermal heat. A thick atmosphere could help, providing insulation, but most detected rogues are thought to be bare, icy worlds. Here is something strange and surprising. Some rogue planets might still harbor liquid water. If a rogue planet is big enough, and if its atmosphere is thick enough, the heat from its core could keep a layer of liquid water alive beneath an icy shell. Scientists have proposed that rogue planets with enough internal heat, much like the moons Europa and Enceladus, could host subsurface oceans for billions of years after being ejected from their solar systems. This means that life, in principle, could exist on a rogue planet, not on the frozen surface, obviously, but deep inside, in the dark, warm water, sealed off from the dead cold above. If true, that changes the entire search for life. The most common place for living things in our galaxy may not be on sunlit worlds around friendly stars. It may be on lonely, ejected planets, drifting in blackness, life hiding in their frozen hearts. The night sky you look up at whenever you glance outside may be full of them, trillions of them. You will never see them. They are too dark, too distant, too cold, just drifting in the emptiness, holding their secrets patiently. Some of those secrets might also be dead, frozen astronauts. On Earth, when a body dies, it returns to the Earth. Bacteria digest it, fungi consume it, insects and scavengers break it apart. Within months, even a carefully preserved body begins to change dramatically. Within years, little remains but bones. In deep space, none of those processes can work. There are no bacteria, no insects, no oxygen, no moisture. The key reason is that decay requires life. Decay is not just a chemical process, it is an ecological one. Microbes, bigger than atoms but smaller than grains of sand, eat the body from the inside out. On Earth, these microbes are everywhere, including on and inside your own body right now. Your gut alone contains more bacteria than you have cells. Freeze that body deep enough, and those microbes stop. An astronaut drifting in space, without a recovery mission, would first lose all of its internal heat over the course of many hours. The body would cool slowly, first the extremities, then the core. At some point, internal temperatures would fall below the freezing point of water. All the liquids inside, blood, interstitial fluid, the moisture in tissues, would solidify. Any bacteria that were alive at that moment would be frozen mid-activity. Their own chemistry requires liquid water to operate. Without liquid, their enzymes stop working. Their membranes cannot carry out their functions. Decay, as Earth knows it, comes to a halt. The body would become a hard, brittle statue, preserved at the temperature of deep space. And here is the eerie part. It could stay that way for a very, very long time. How long? In the absence of bacteria, the main threats to a frozen body in space are radiation and micrometeorites. Radiation, especially ultraviolet light and cosmic rays, would slowly degrade the exposed surfaces over many thousands of years. Skin and hair would darken, then tougher layers would slowly break down. But this is a slow process, much slower than Earth's biological decay. Micrometeorites are tiny grains of rock that travel at very high speeds. Even grains smaller than a grain of sand can punch small craters into exposed objects. Over millions of years, a body would slowly become pitted, scarred, and eventually broken apart. But short of a direct collision with something large, the body would remain recognizable for perhaps 100,000 years or more. Its features intact, its clothing intact, its expression intact. On Earth, nothing lasts like that. Even the best preserved mummies are thousands of years old, not tens of thousands. Even under ice, biological processes continue slowly. In space, they stop. This has practical implications for space travel. If an astronaut dies on a long mission, the crew has serious decisions to make. The body cannot be buried. It cannot be cremated without using valuable resources. Leaving the body in the vessel creates ethical and logistical problems. Ejecting it into space creates a new problem. A frozen crew member, preserved and traveling on its own trajectory, could become a hazard to other spacecraft in the future. So, cold does more than kill. It remembers. Every dead thing in space is still, in some sense, present. Every broken machine, every abandoned satellite, every dead astronaut, in the unlikely case that this ever happens, stays preserved far longer than anyone on Earth could imagine. The universe, in its silence, is a vast archive of frozen artifacts, and cold is the librarian. It keeps the books. It does not lose them. Absolute zero is the lowest temperature theoretically possible. On the Fahrenheit scale, it is exactly minus 459.67 degrees. On the Kelvin scale, which scientists prefer, it is 0 degrees, a clean, simple zero. At absolute zero, by definition, there is no thermal energy left. Every atom has stopped moving. Every vibration has stopped vibrating. Nothing can get colder because there is nothing left to take away. Except, in reality, absolute zero cannot actually be reached. Not in nature, not in any laboratory, not anywhere. This is not a technical limitation. It is a law of physics. The third law of thermodynamics says that as you cool a system toward absolute zero, it becomes harder and harder to remove the remaining heat. Each step closer requires more effort than the last. The final step, to reach zero exactly, would require infinite effort. No machine, no process, no trick in the universe can ever cross that line completely. Think of it as a sand pile. As you shovel sand off the pile, each shovelful gets harder to reach. At the bottom, the last few grains would require you to dig endlessly into the ground to extract them. You can approach the last grain, but you can never actually remove it. Quantum mechanics adds another layer. According to Heisenberg's uncertainty principle, there is a fundamental limit on how precisely we can know both the position and the momentum of a particle. If all atoms in a system stopped moving completely, we would know both their position and momentum exactly. That is not allowed. So even at temperatures approaching zero, a small flicker of motion remains. This is called zero-point energy. Zero-point energy is the last rattle of the universe. No matter how cold something gets, atoms jiggle, just a tiny bit, because they must. Despite this, scientists have come remarkably close to absolute zero in the lab. Using elaborate systems of lasers, magnetic fields, and evaporative cooling, researchers have cooled small samples of atoms to within a few billionths of a degree of absolute zero. This is colder than deep space, colder than the Boomerang Nebula, colder than the background radiation of the entire universe. At those temperatures, atoms behave in ways they never do at room temperature. They can merge into a single shared quantum state, called a Bose-Einstein condensate. All the atoms in the sample act as if they were a single enormous atom. Light passes through them strangely, slowing to walking speeds or stopping entirely. The boundary between classical physics and quantum physics dissolves. Cold, in other words, reveals the true nature of matter. At room temperature, chaos hides it. Heat blurs the underlying structure, cool things down enough, and the universe shows its bones. Absolute zero is not just an end point. It is an ideal, a limit that nature approaches but never quite reaches. It sits on the edge of reality, like a cliff no one can fall off, because the closer you get, the more the cliff retreats. And that is perhaps the most elegant fact about cold. It is infinite in a way warmth never is. You can always get warmer. There is no upper limit to heat. But cold has a flaw no one can stand on, a flaw no one can even quite touch, forever. At room temperature, atoms are in chaos. They spin, shake, bounce off each other, collide, vibrate, and swap places constantly. The warmth you feel is just your skin picking up these small impacts, billions of them every second, at the surface of every object you touch. Cool things down, and the motion slows. The atoms bounce less often, the shaking gets smaller. Approach absolute zero, and you might expect the motion to stop altogether. Quantum mechanics says it cannot. This is one of the strangest and most firmly confirmed facts in physics. At the deepest cold we can reach, atoms continue to move. A tiny, ghostly, unstoppable motion. It is called zero-point vibration, and it is a direct result of the uncertainty principle. Here is the idea. According to quantum rules, if a particle had both a perfectly known position and a perfectly known speed, we would be able to predict its future exactly. Reality does not allow that. A particle that is perfectly still, sitting perfectly in one spot, would have both zero momentum and a definite location. That is forbidden. The universe refuses to allow a particle to be that precisely defined. So, the atom fidgets. It has to. Even in the coldest place possible, the atom is slightly uncertain about where it is and where it is going. That uncertainty manifests as a tiny, irreducible motion. No matter how much energy you remove, that fidget remains. The amount is small, but it is real. In some materials, zero-point motion is large enough to cause strange physical effects. Helium, for example, is a light atom with weak bonds between its particles. At temperatures close to absolute zero, its zero-point energy is big enough to keep it from freezing solid under normal atmospheric pressure. Helium is unique in this way. It stays liquid right down to absolute zero itself unless you squeeze it with extra pressure. This is not just a curiosity. It has practical consequences. Liquid helium is used in medical MRI machines, in particle accelerators, in advanced electronics labs. It is the working fluid of the coldest technologies humans have ever built, and it only works because of zero-point motion. Cold also reveals another quantum phenomenon called superfluidity. When helium is cooled below about -455 degrees Fahrenheit, it enters a strange new phase. It becomes a superfluid. It flows without friction. It can crawl up the walls of its container and climb over the rim. It can seep through openings smaller than an atom. It can spin forever without slowing down. All of this comes from the quantum nature of reality expressing itself in the deep cold. At warm temperatures, each atom is on its own. In the deep cold, atoms start to share quantum states. They merge their identities. They stop being individual particles and become something more like a single giant wave. This is the hidden face of the universe. The face it only shows when heat steps aside, and it means something profound about the universe as a whole. The very act of being cold is not a lack of motion. It is a different kind of motion, a quieter, deeper one. The stillness of cold is an illusion, hiding the quantum buzz underneath. Even the coldest atom in the most carefully cooled laboratory on Earth is, in a sense, still dancing, just in a language almost too small for us to hear. On a quiet research floor at a university in Colorado, machines hum day and night, inside sealed chambers wrapped in layers of insulation. Inside those chambers, scientists have done something the universe itself has almost never done. They have cooled atoms to a temperature colder than anything in deep space. We are talking about temperatures only a few billionths of a degree above absolute zero, far below the cosmic microwave background, far below anything that has ever happened naturally on any planet, any moon, any nebula, or any vacuum between stars. This is confirmed. Experiments like this have been going on for decades, at labs including Gila in Boulder, MIT, and elsewhere around the world. Awards have been given for them, including several Nobel Prizes. How is it possible? The trick is a combination of two amazing techniques. The first is laser cooling. The second is evaporative cooling. Laser cooling sounds like a contradiction. Lasers are supposed to heat things up, not cool them down. But in this strange method, photons from a carefully tuned laser can actually slow down moving atoms. When an atom moves toward a photon of exactly the right frequency, the photon pushes back against it. Repeated collisions, billions per second, gradually bring the atom almost to a halt. The slower it moves, the colder it gets. Scientists use 6 lasers, pointed at each other from all directions, to surround a small cloud of atoms. The cloud gets squeezed into near stillness, like a tiny cluster of bees caught in a beam of light. Laser cooling alone can only take you so far. To go even colder, researchers use evaporative cooling. They let the hottest atoms, the ones still moving the fastest, escape from the trap. What remains is a colder, slower cloud. Repeat again and again, and the cloud keeps losing its warmest members. The survivors get cooler and cooler, until only a tiny pocket of almost motionless atoms remains. At these temperatures, the laws of physics change. Atoms can merge their identities into a Bose-Einstein condensate, a state of matter predicted by Albert Einstein back in the 1920s but not observed in a lab until 1995. In a condensate, all the atoms share a single quantum wave. They stop behaving like little balls. They start behaving like one spread-out entity. Inside these condensates, light itself can be slowed to walking speed. Atoms can tunnel through barriers that should stop them. Superfluids can flow forever without friction. These are not science fiction ideas. They are measured, filmed, and tested over and over in working labs. One experiment cooled a sample to less than 1/10 of a billionth of a degree above absolute zero. That is colder than anywhere in the known universe, outside of a lab. There is even a space lab for this. The Cold Atom Laboratory, aboard the International Space Station, was installed in 2018 to push these experiments even further. In microgravity, the atoms can be held in shape longer without falling away, allowing for even deeper cooling. The ISS is now home to the coldest known place in the universe, at least for seconds at a time. This is astonishing. The coldest point in the cosmos is not out among the stars. It is above our heads, circling the Earth, built by human hands, and cold, in this form, may be one of our most powerful tools for discovering what the universe really is. Black holes seem like the most violent objects in existence. They tear stars apart. They launch jets of gas at nearly the speed of light. They warp space and time around them. They bend light into rings. They sound, by every reasonable measure, like cauldrons of energy. And yet, physicists believe that black holes are among the coldest objects the universe will ever produce. This is not an obvious fact. It took a young British physicist named Stephen Hawking to work it out in the 1970s, using a combination of general relativity and quantum mechanics. His result, now called Hawking radiation, is still unverified by direct observation, but it is widely accepted among physicists as very likely to be true. This is a theory, powerful, but not yet confirmed in the same way as the cosmic microwave background. Here is the idea. Around the event horizon of a black hole, the boundary beyond which nothing can escape, space itself is never truly empty. Quantum fluctuations cause pairs of particles to pop in and out of existence constantly. Normally, the pair annihilates immediately, but near a black hole, one particle can fall in while the other escapes outward. The particle that escapes carries away a tiny bit of energy. That energy, in the long run, is drained from the black hole itself, which means the black hole is slowly losing mass. Slowly, very, very slowly, but continuously. This energy loss can be described as a temperature. It turns out the temperature of a black hole is inversely proportional to its mass. The bigger the black hole, the colder it is. For a stellar black hole, a few times the mass of the Sun, the temperature is incredibly tiny, on the order of 100 millionths of a degree above absolute zero, far, far colder than the cosmic microwave background. And for the supermassive black holes at the centers of galaxies, billions of times the mass of the Sun, the temperature is even smaller, nearly indistinguishable from absolute zero. This has a strange consequence. Because the cosmic microwave background is still warmer than these giant black holes, they are gaining more energy from the background than they lose through Hawking radiation. Right now, big black holes are still growing slightly, on average, feeding on the ambient warmth of the universe. But that will not last forever. The universe is expanding. The cosmic microwave background is cooling. In the far future, trillions of years from now, the background will drop below the temperature of even the largest black holes. At that point, the the black holes will start to lose energy to the background. They will begin to evaporate. It will take an unimaginably long time. For a supermassive black hole, full evaporation would take a number of years so large that it cannot be written in normal form. It is a 1 followed by dozens of zeros, but eventually, every black hole in the universe will evaporate. Each one will flicker, then fade, releasing its remaining energy as a faint hiss of radiation. When the last black hole dies, the universe will be emptier and colder than it has ever been. No stars, no galaxies, no heat, just a faint background of radiation stretching into near nothing. Darkness and silence, forever. That is the direction the cosmos is going. Slowly, deliberately, inexorably, toward cold. Right now, the universe is warm. Stars burn, galaxies glow, planets bask in the radiation of their suns. This moment, in cosmological terms, is a tiny, bright flicker in the life of the cosmos. That flicker is ending. Not soon, by any human measure, but inevitably. Physicists call the ultimate future the heat death of the universe, a grim name for a gentle fate. It is not an explosion. It is not a collapse. It is a slow, endless cooling, spread across timescales longer than the human mind can properly hold. Here is how it unfolds, according to our best current theories. For about the next 100 billion years, the universe will look similar to how it looks now. Stars will form in star-forming galaxies. Old stars will die. New stars will be born. Planets will exist. Some will harbor life. Galaxies will slowly merge with their neighbors in local groups, forming larger, stable systems. After that, star formation will slow. The gas needed to make new stars is being used up. Existing stars will continue to burn, but no new ones will be born. The sky will get dimmer as existing stars die off. By around 100 trillion years from now, the last star will go out. That number is hard to imagine. 100 trillion. The universe right now is only about 13.8 billion years old. So, the final star will not burn out until the universe is nearly 10,000 times older than it is today. After the last star dies, the cosmos will enter what scientists call the degenerate era. For trillions and trillions of years, the only objects left shining will be the cooling corpses of former stars. White dwarfs slowly fading, neutron stars radiating away their last heat, brown dwarfs quietly drifting through the dark. Over even longer timescales, atomic matter itself may begin to decay. Protons may slowly break down. Matter, as we know it, may dissolve into loose particles and radiation. Eventually, only the supermassive black holes at the centers of old galaxies will remain as the largest coherent objects. And as we saw, even they will evaporate over spans of time that dwarf everything else. On the order of 1, followed by 100 zeros years, once the last black hole is gone, the universe will be an empty, thin soup of radiation and a few scattered particles. The temperature will be infinitesimally above absolute zero. There will be no structures, no stars, no planets, no life. Only cold, quiet, patient darkness, stretching out forever. This is the heat death, not a dramatic end, a soft, endless fade. Some physicists hold out hope for other possibilities. A big rip, where expansion tears the universe apart. A big crunch, where expansion reverses and everything collapses. A big bounce, where our universe is just one in a chain of births and deaths. These are theories, each with supporting arguments, but none is confirmed. The most mainstream view, consistent with everything we have measured about dark energy, is that the universe will keep expanding, cooling, and thinning forever. And at the end, the temperature of the cosmos will drop closer and closer to the floor that nothing can ever quite reach. The universe will be colder than any moment that came before, colder than the background radiation of today, colder than the coldest nebula, colder than anything we have ever seen. And life, if any remains, will have to find new ways to exist. Picture this. You are standing on a rocky planet, incredibly far in the future, trillions upon trillions of years from now. The sky above you is not the sky you know. There is no sun. There has not been one in this region for a very long time. The other stars, once bright and scattered across the heavens, are dim red points, barely visible. Some have already gone out. Soon, all of them will. This is the era of the last stars. According to our best understanding, star formation cannot continue forever. Stars are built from clouds of gas, mostly hydrogen left over from the Big Bang. Each new star uses up some of that gas. When a star dies, some of the material is recycled into new stars, but not all of it. Some is trapped in white dwarfs, neutron stars, black holes, and planets. Some is locked up forever. Over hundreds of billions of years, the amount of fresh hydrogen available to make new stars will keep shrinking. Galaxies will fade. New suns will stop being born. The only stars still burning will be the ones already lit. Among those, the longest lived are the red dwarfs. Small, cool, dim stars that burn their fuel so slowly they can live for trillions of years. Most of the stars in our galaxy are red dwarfs. They are faint, easy to overlook, and they have staying power no other star can match. Our own sun, by contrast, has a predicted total lifespan of about 10 billion years. A red dwarf 1/10 its mass might live for a trillion years or more. A red dwarf 1/20 its mass could survive for several trillion years. Still, even red dwarfs must eventually exhaust their fuel. When the last one cools, the universe will have no main sequence stars left, no classical suns, no ordinary burning points of light anywhere. After that, the only things shining in the sky will be the fading remnants of former stars, white dwarfs, slowly radiating away their last heat over quadrillions of years. Neutron stars, spinning down, getting dimmer as their energy drains. Brown dwarfs, which never quite caught fire, sitting in the dark with a faint internal glow. Eventually, even these will cool. White dwarfs will become black dwarfs, theoretical objects that no longer emit visible light. No black dwarf has ever been observed, because the universe is simply too young for any to exist yet. A white dwarf takes perhaps a quadrillion years to cool completely. None has been around that long. They are still out there, waiting. When the black dwarfs finally form, everywhere, the visible sky will go dark, not just at night, all the time, everywhere. There will be no daylight, no starlight, only the faint infrared glow of cooling compact objects and the ever-weakening background radiation of the Big Bang. If there is life in that era, it will have to hunt for heat in strange places, near black holes, where Hawking radiation still provides a whisper of energy, near decaying particles, if the theories are right, near the last sparks of matter rearranging itself. And these would not be ordinary biological creatures. They would be civilizations that have figured out how to harvest energy gradients of almost unimaginable subtlety. Beings that have survived, somehow, across spans of time far greater than the current age of everything. Or, most likely, there will be no life at all. Just quiet, cold space, waiting for the last flickers to end. Imagine the universe, trillions upon trillions of years from now. No stars, no galaxies, no light, only an empty, cooling soup of thin gas and stray particles, drifting through a space that has kept on expanding. Something strange starts to happen to the matter itself. According to modern physics, this is a theory, not a confirmed observation, but it is what the mainstream models predict. At some extremely long timescale, the particles making up ordinary matter may begin to break down. Take protons, for example. Protons are the building blocks of every atomic nucleus. They are the reason hydrogen is hydrogen and carbon is carbon. Without them, there are no atoms. Without atoms, there are no molecules. Without molecules, there is no chemistry. Without chemistry, there is no life. For a long time, physicists assumed protons were perfectly stable. They were wrong, maybe. Theories of grand unification predict that protons can decay on their own into lighter particles, given enough time. The half-life of a proton, in some models, is around 10 to the 34th power years. That is a 1 followed by 34 zeros, a number so large it has no human meaning. But across the unimaginable span of the heat-death era, even such tiny decay rates matter. Over vast timescales, matter may slowly disappear. Atoms will dissolve into showers of smaller particles. Electrons will drift off. Photons will stretch thinner and thinner as the universe continues to expand. If proton decay is real, then everything you know, every rock, every cloud, every drop of water, every cell, every person, is temporary in a way deeper than biology. Not just living things decay. All matter, in the end, does too. Next, consider the effect of the expanding universe. As space itself continues to grow, particles move apart from each other. The density of matter drops. The density of light drops. Eventually, the universe becomes so vast and so thin that encounters between anything are extremely rare. Temperatures fall with expansion. Every particle loses energy, slowly, as it redshifts along with the stretching of space. The background radiation that once warmed the cosmos becomes fainter and fainter. Any remaining heat radiates away, weaker and weaker, until even the faintest trickle of warmth is gone. Eventually, the cosmos may reach a state called maximum entropy, a state of perfect disorder. Energy, in a useful form, no longer exists. There are no gradients left to drive any process, any chemistry, any life. In this state, matter itself, in any complex sense, is gone. What remains is a thin, cold bath of radiation and elementary particles, so spread out that nothing ever meets anything else. Time continues to pass, technically, but no changes happen. Nothing can change. There is nothing left to change. This is the deepest kind of cold imaginable. A cold that is not just a temperature. A cold that has consumed structure itself. A cold that has erased the difference between one place and another. Physicists sometimes call this the final equilibrium. It is a state from which nothing new can arise, without some entirely unknown process stepping in. Some theories speculate that quantum fluctuations in this frozen infinity might eventually, after timescales beyond comprehension, give birth to new universes, new big bangs, popping into existence in the deepest cold. If true, then our own cosmos may be one child in a chain of universes, each born from the final chill of the one before. This is pure speculation, but it lingers as an idea. After every journey through temperature we have taken, one question remains. What is the universe actually like when you step back far enough? We live inside a moment of unusual warmth. Stars shine around us. The sun pours energy into Earth. The ground beneath our feet holds on to that warmth, day and night. Liquid water rolls across our continents. Plants grow, animals breathe, cells divide, thoughts form. All of it depends on heat, on gradients, on differences between hot and cold that can be harnessed to do work. Without those gradients, no engine can run, including the engines of life. But look at the big picture, over the full lifetime of the universe, and something shifts. The warmth, the stars, the galaxies, the planets, the biology are all tied to a small, narrow phase of cosmic history. A few 100 billion years in total, out of an expected future that runs into numbers with dozens of zeros. In that grand stretch of time, the warm era is a short opening scene, a brief, fiery prologue. Everything that follows is cold. Once the stars die, once the black holes evaporate, once matter itself begins to decay, the universe will spend the vast majority of its existence in a frozen, quiet state. If the heat-death theory is correct, most of cosmic history takes place in darkness and near absolute zero. Measured by time, cold is the rule, warmth is the exception. This is a strange way to think about the world you know. Everything that feels solid, everything that feels alive, is a short-lived exception to the universe's true baseline. The cold is the background. It was there before the stars lit up, in a certain sense, and it will be there when they are all gone. There is a flip side. If cold is the natural state of things, then warmth is a rare, precious thing, not just poetic, measurable. Every warm object in the cosmos is a local defiance of the bigger picture. Every sunlit day on Earth is a tiny, glittering anomaly in a cosmic ocean of frost. This changes the weight of ordinary moments. A hot cup of coffee on a cold morning, the warmth of a hand in yours, a fire in a fireplace. These are not trivial comforts. They are small wins against the dominant temperature of the universe. They are sparks carved out of a much bigger chill. Life itself, seen this way, is a pattern that refuses to cool down. For billions of years, our planet has managed to keep its temperature stable. Not too hot, not too cold, just right for liquid water, for cells, for brains. The reason that pattern persists is that our sun is still burning, and the Earth has a convenient atmosphere to hold the warmth in. That will not last forever. In 5 or 6 billion years, the sun will swell into a red giant, cook the Earth, then collapse into a white dwarf. What is left of our planet, if anything, will eventually join the slow cooling of the cosmos. Cold is patient. It is not angry. It is not cruel. It is simply there, waiting, under everything else. It is the fabric, the background, the quiet state the universe settles into when no star shines to disturb it. And so the final truth, unsettling but honest, is this. The universe is cold. It has always been mostly cold. It will be almost entirely cold for most of its existence. You live in a warm bubble. Make it count.